Good afternoon, everyone. Thank you very much for coming. Today we have our own Phill, so it's always great to have someone from here. Phill and me just spoke on the fact that when he was undergrad, that he did it here also at UNSW. I tutored him on the energy efficiency course, and he did such a great project on how to save energy from the gym. It's like quite long, almost like a PhD to read. But Phill was a great student back then. He did great PhD here with Stuart. And then he had a postdoc position in Oxford. We are lucky that he came back last year and joined us again. As you know, he's an expert for hydrogenation, and because of that we asked him to share some of his knowledge on hydrogen and modeling. So Phill, thank you very much for coming. It's great to host you.
Okay.
Welcome, Phill.
Okay, so I'm going to give a talk on hydrogen redistribution, which is the main focus of my ACAP fellowship, which is why I'm back here, I guess, for the next couple of years. It's going to be a little bit rough and ready. It contains some new ideas and a fair few thoughts that haven't been completely tested out yet, so I'm hoping to get a bit of feedback on those. So I'm hoping people will find it interesting, and if you like hydrogen, you probably will. If you don't like hydrogen, this is going to be a long talk. So, a bit of an outline of what I'm going to go over. Very, very quick introduction to hydrogen and silicon. Given the expertise present at this university, I'm not going to go into a long detail of how it's used in silicon, where it comes from, what we use it for. I'm going to give a very quick introduction and then get into the main topic here, which is the simulation and the redistribution of hydrogen during thermal processing, and some of the effects we are beginning to see in solar cells that might be linked to this. So those effects include the contact resistance, the front contacts. We've actually been able to turn solar cells into quite effective resistors through a thermal process after firing, and some surface degradation we're seeing recently, which is not yet an issue for cells in the field, but might be with future cell architectures. And then I'm going to get a bit theoretical on what some of the causes of this surface degradation might be. So I felt I had to include this slide. I was going to include it in my IEEE presentation last year, because my colleague at the time, Sebastian over in Oxford, read my paper draft and said it read like a love letter to hydrogen. It was just all about, you know, the difficulty in seeing hydrogen, difficulty in having a good relationship with it. And to this day, I don't have a good relationship with hydrogen, because it can do amazing things. It can obviously, you see at the top there, a couple of PL images, massive improvements in bulk lifetime multicrystalline solar cells, improved surface passivation. We use it to get rid of the boron-oxygen defect. And to be honest, we can't really get rid of it. Every chemical process we do, we put it in a acidic etch, we're going to introduce some hydrogen. So there's always a question of not whether you've got hydrogen, but how much you've got. The problem is it does all these things while remaining well below most detection limits. Because you can't get rid of it, you can't even get rid of it in vacuum systems, so the detection limit for hydrogen is much higher than many other impurities in silicon, so we just cannot see if it's there. So a lot of our arguments are based on the inferred presence of hydrogen. It's also a bit of a flirt. It interacts with just about everything in silicon. Interstitials, impurities, vacancies, you name it, hydrogen interacts with it, which creates a third problem, which is then to establish the fundamental properties of hydrogen in silicon is by no means trivial. You can't be sure if what you're observing is interstitial hydrogen or interstitial hydrogen interacting with oxygen or something else entirely. So this means some of the most basic properties aren't well established, and I'll discuss a couple of those in a little bit. And for a long time, we thought hydrogen was just great. We just put it into silicon, it did its thing. We got defect passivation. We could fiddle with that and improve it. But obviously, in the last few years, I'm sure people who've been at UNSW for a while have heard various presentations blaming hydrogen for LeTID and other things, and for degradation in solar cells. So we've encountered a few instances in which it doesn't work for us. Now, these properties lead you, like any bad relationship, to start making excuses for it. So a few warnings about what you'll encounter in this presentation. There'll be the odd circular argument, where I say we can learn something about hydrogen from this process, which we think is hydrogen because it looks like hydrogen. There's also a bit of speculation, as I've said. Again, we infer the properties. And finally, because I can't present very nice images of location, etc., there's going to be a lot of graphs. So getting started on the graphs. This is the basis of the hydrogen simulation model I developed over the last couple of years, which is reasonable for predicting the general behaviour of hydrogen. We simulate hydrogen, the interstitial hydrogen charge states, so we have the negative, positive and neutral charge states. And in the top right corner, you can see the energy level of up top should be the donor and acceptor levels. So it's a negative U impurity. So the donor level is quite near the conduction band edge, whereas the acceptor level is quite near the middle of the band gap. Which means in P-type silicon, we almost always have H plus being the dominant charge state, whereas in N-type silicon, we can have H minus. However, with temperature, we can again change that to H plus. And the fractional concentration is the function of the Fermi energy level, as presented in the bottom right corner. We also simulated the formation of hydrogen dimers, so at least 3 forms of hydrogen dimers we can get with varying stabilities and diffusivities, as well as the pairing with dopant atoms. Ideally, we'd also include interaction with oxygen, which are pretty well known, vacancies, and possibly carbon, but that's to be known over the next couple of years. One of the critical things we have to simulate is the interaction with electric fields. So hydrogen, being small, a low mass particle, but also charged, is very strongly affected by electric fields, and because it's a charged particle itself, can change internal electric fields if it's in high enough concentration. So these are simulations from a couple of years back where we simulate the introduction of hydrogen to an NP structure, so a phosphorus diffusion or a boron bulk, and we simulate hydrogen moving in. And rather than a simple diffusion profile, we obviously get a slightly more complex structure. So you can see that the majority of the hydrogen that's gone in is trapped in that surface layer near the surface. And if we look at what form it's in, it's largely bound to the phosphorus dopants, which is unsurprising given the concentration of those traps that is present. In the bulk, we largely have hydrogen present as dimers. We don't expect at 300 degrees the majority of hydrogen to be in the interstitial form. However, it's interstitial form that's actually driving the diffusion and the transport. So if we look at the interstitial form, we have our H minus, H plus, and a very small concentration of hydrogen in the neutral charge state. A lot of research effort around here has gone into getting more hydrogen neutral charge state because we think it's quite beneficial for defect passivation, but in almost any condition we expect it to be lower concentration than either of the charge states. And what we have is this crossover point here. So in the left-hand side of this crossover point, we have a dominance of H minus. And given the prevailing electric field in that region, that causes quite a steep concentration gradient because the electric field is wanting to push that hydrogen back towards the surface. So you get quite a steep diffusion gradient in order to actually have net transport of hydrogen into the bulk. On the other hand, once you reach this crossover point, you get H plus, the same electric field will sweep that into your solar cell and you have very few transport barriers from that point further in. And we can see here the electric field. Unfortunately for us, this crossover point is typically in one of the areas of high electric field, so we do get this very severe dip down to the crossover point. Trapping complicates this a bit, so while we can get most of the kinetics from this, if you have a higher effective solubility for hydrogen on one side of this crossover point, the other one, you'll also distort the total hydrogen profile somewhat. So this is simulating it coming in, which is what I was doing initially. The other point is that this crossover point is going to be on the N-type side of the metallurgical junction. So again, due to the asymmetry of the donor and acceptor levels of hydrogen in the band gap, the level will always be in the N-type region, which becomes important later on when we consider these surface degradation effects. Now, if we increase the temperature, again, because of asymmetry, what we do is we shift this crossover point closer to the surface. So at 700 degrees, which is still a bit low, but closer to typical firing temperatures, we can see this crossover point for the H plus and the H minus is now significantly close to the surface, and the ratio of hydrogen at the surface to the bulk concentration of hydrogen has shifted dramatically. And this is what drives the hydrogen redistribution I'm going to talk about later. So when we go back down in temperature, this ratio will tend to move back towards a greater value. Hydrogen will move from the bulk of the silicon towards the surface. And I'll present the simulations on that in a moment. This is just going through that. It's also complicated a little bit by the amount of hydrogen trapped at phosphorus. So at higher temperatures, because of the extra thermal energy, we have less hydrogen in its bound forms. So we have a greater proportion of interstitial hydrogen to hydrogen trapped at phosphorus. Again, this proportion will decrease at lower temperatures, so that will suck even more hydrogen into that very heavily doped region. So I'm going to get into the effects now briefly and then show some of the simulations of this redistribution taking place and how it correlates with this particular effect. So this was observed here by Chen, who's wandered in at some stage. And it was a bit of a pain at the time. So this has complicated some of our efforts to get rid of LeTID, or degradation, multicrystalline silicon, significantly. There's some great thermal processes both Catherine and Chen have worked out and come up with that can completely eliminate your degradation in your bulk silicon, that can make it like it was not there at all. The problem is, as you can see here, your fill factor can undergo a catastrophic decrease. So while you prevent maybe 5 to 10 degrees of degradation in performance due to lifetime changes, you can lose something like 20% in terms of your fill factor, and that's not really coming back. So this was identified as being due to contact resistance at the front metal contact. So the screen printed silver fingers on your N-type emitters in a PERC solar cell, the contact resistance there is going up by orders of magnitude during these processes. This effect is also, as we go here, unstable. So with enough current pass through it at low temperatures, you can temporarily reverse it, and you can also reverse it at high temperatures. So for any good hydrogen conspiracy theorist, this is enough to indicate that hydrogen might well be involved. So we carried out some in situ measurements to actually see if we could learn anything about hydrogen or try and confirm whether hydrogen was involved in this process. So we've got a PERC solar cell there. We create contacts to the front and back, just simple probes, and we do a 4-terminal IV measurement. Now, typically this takes several hours to do, to see the effects at their greatest, and we do see very dramatic effects. However, even in the first half an hour or so, we've got enough to really degrade your solar cell performance. So what we tend to get is something like this. So we start out with something that looks pretty diode-ish. If you ask PC1D to tell you what a diode looks like at 300 or 400 degrees, it'll spit out something pretty similar to that initial curve, probably a slightly lower reverse bias current, but we can explain that. By the end of the process, what you've got is a pretty flat line. So in the dark, it looks exactly like a resistor. The diode properties are pretty much unimportant compared to the series resistance we have here. And this is all at that front metal contact. So we simulate this. So for this presentation, the bottom right corner is the more important one, where we simulate what happens to a uniform initial distribution of hydrogen when we then anneal it, in this case at 350 degrees, starting off with zero bias. So experimentally in the bottom left, you can see an increase in contact resistance over time and the electric field at the top. So we simulate this and we get this redistribution, again driven by that crossover or inflection point where H plus from the bulk is being sort of drained out there to add to the H minus of the front surface. And we can see over our simulations, we can simulate this to redistribute hydrogen over quite a large range. So given long enough, we could redistribute hydrogen from the entire bulk region towards the surface. Experimentally, we then play with the bias. That's our easiest way to see if we can put a bias on it, see if we can move hydrogen either towards the contacts or away from the contacts. So if we put a forward bias on it, we saw a massive increase in our series resistance and the rate of our series resistance. And this is driven, well, this is largely explainable because in the top left you can see the resulting electric field from this forward bias. We've reduced the electric field across the junction, so what you expect in forward bias, and especially we reduced it on the right hand side, so into the p-type material. So this is where the hydrogen is in the positive charge state and where an electric field would repel it away from the surface. So as a result of that electric field in that region being decreased, we can see it as a much smaller dip from the sort of bulk concentration down to our crossover point. And this allows far greater redistribution of hydrogen to the front surface, as shown here. If we then apply a reverse bias, you would expect a greater electric field in that p-type region, and hence H plus to be repelled away and us to have less contact resistance increase. And rather fortunately for the purpose of this presentation, that's exactly what we see. So if we apply a high enough reverse bias, we can almost completely suppress this contact resistance increase, and we have no effective change in series resistance. And again, you can see here, if I go 2 more on, there's now a very steep gradient for H plus approaching that inflection point, and comparison there with hydrogen with a positive charge applied. So we can simulate this. Our experiments in general behaviour agree with it. So it's quite likely that hydrogen might be involved, or at least the charged species similar to hydrogen is involved. There's a couple more fingerprints of hydrogen that also lead us to believe that this redistribution might be taking place. So one of these is reversibility. So while these effects persist at room temperature, again, you can put a reverse bias on, you don't see any significant increase in your series resistance after the process, whereas with forward bias you do. But more importantly, you can reverse it. So if you take the same cell and you put them back under forward bias, if they were previously under forward bias, we seem to see them go up faster. So there's some long-term or long-range effect from our process. But we can then apply reverse bias at the end and actually almost completely reverse this increase, which is a usual fingerprint of hydrogen's involvement in this reversibility. And usefully, if we do reverse the increase in series resistance by applying a subsequent bias, we then actually see at room temperature, we don't see a significant increase in series resistance. So we started out with values of about 0.6. So rather than going up by orders of magnitude, you've gone up by a very small amount. The problem with this a little bit is, while we can simulate it, we don't know whether what we're seeing is due to all the hydrogen leaving the bulk moving to the surface, which would then give us useful information on what we're doing to get rid of LeTID, or whether only a small amount is. And this depends on the bound states of hydrogen in the bulk. So there's a few different forms we could use. So this simulation is just considering hydrogen bound at dopant traps. So it redistributes very quickly, and we do get significant long-range redistribution of hydrogen. However, if we consider a trap where there's a fixed ratio and only a small amount of the hydrogen in the structure is interstitial during the process, then we can see, while we still get the build-up at the surface, we don't redistribute that much from the bulk. Or we can have a scenario where we have a very slow release of hydrogen from our bound forms in the bulk. And in this case, while we would have a slower increase at the surface, we would over time be able to much more effectively redistribute hydrogen from the bulk. And this last sort of option is the most likely we see. So we do see evidence that we have denuded the bulk of hydrogen. Not only do we not see LeTID, which we think is related to hydrogen in the bulk, we also can't regenerate the boron-oxygen defect, which is another hydrogen-related effect in the bulk. So both of those go away if we do this process for long enough, which indicates most of the hydrogen is either gone or in a very stable state in the bulk. One thing before I jump ahead is that potentially from this rate of change of the series resistance, we might then be able to learn something about the hydrogen bound forms in the bulk. So this is where the argument gets a bit circular. But if it changes depending on the bulk material, you could then infer that the bulk bound form of hydrogen in the bulk material is different. So it should be different for N-type bulk or P-type bulk or monocrystalline or multicrystalline. So we did try it with a few different samples, which were mono and multicrystalline cells, and we used ALBSF and PERC, with the assumption that ALBSF will contain less hydrogen than PERC, so the effect should be less pronounced. And fortunately, results came out more or less as we expected. So this is PERC, and what you can see here is the monocrystalline cells actually degrade worse than the multicrystalline in terms of this contact resistance, but the temperature dependence of that degradation is nowhere near as pronounced. So this would be consistent with the bound form of hydrogen in the monocrystalline bulk having a lower binding energy than the bound forms of hydrogen in the multicrystalline bulk material, which again, via circular argument, we expect because that's what we think it should behave like. We think there are more sites and more deep binding energy sites for hydrogen and multicrystalline bulk material. So we can fit this, put it into our Arrhenius plot, and again, we get what we expect, so we're happy. So we find that monocrystalline material, monocrystalline PERC, degrades the fastest and has the lowest temperature dependence, which is matched by ALBSF cells. So in this case, we expect a lower bulk hydrogen concentration, but the bound form should be the same because the bulk material is the same. And we get almost exactly the same activation energy for this process. I should caution using those energies as anything physically meaningful, because that's not only going to include the binding energy of the defect in the bound form, it's going to include the energy for transport to the surface, as well as any activation energy of the process itself that's going on at the contact. But the fact that everything else is the same except for ASLB's PERC, and we get the same activation energy, is nice. And with multicrystalline silicon, we get a much higher activation energy, both for PERC and ALBSF. In the case of multi, there's less of a difference between perk and LBSF, and I can go into that another time if people want to discuss why that might be, but it'll be related to the greater number of deep traps in the bulk, which would then trap the hydrogen more effectively during firing. So, the last point, I mentioned it was reversible sort of on a long time scale. We could take a cell that had the problem and reverse it over a few hours. It's also very reversible on a very small time scale. So you can actually sort of toggle it between two states in a matter of seconds in many instances. So in these plots, the open circles show what would happen if we held the cell either at forward bias or reverse bias throughout the entire process. And the closed symbols are where we actually toggle it between the two. So we keep it at forward bias for a while, switch to reverse bias, back to forward bias, back to reverse bias. And what do we find? We find it's very easy to toggle between these two apparent states, which again gives us an indication that hydrogen or something similar is involved because it is so reversible. We do also see this general increase over time, which indicates that the contacts are either more susceptible to the motion of hydrogen, or there's another effect that's causing a long-term increase in contact resistance. Now, having shown you all this data and saying how nicely it agrees with what we expect, I should note that the delta RS I've been using here, the unit, the increase in series resistance, increase in contact resistance, isn't actually terribly physically meaningful. And the reason for this is on closer inspection of the contacts, we found what I guess you'd expect when hydrogen goes close to interface, that is fundamentally a Schottky contact. So over time, when you get the really bad degradation, we can actually start to see the Schottky characteristics of the silver silicon interface start to appear. So we start to get a significant curve in the IV data, and what you end up then is having two diodes effectively back to back, hence why no current flows. But it's the properties of that Schottky contact that we really need to actually probe in terms of the barrier height and the number of interface states that gives us the physically meaningful data, which then allows us to get extra information about the motion of hydrogen. So the second effect I'm going on to is degradation at the surface. So this is largely based on work out of the University of Constance. David Sperber's the guy who's basically driven this train for a while. And what they observed are, after LeTID has come and gone and your bulk has fixed up, you then start to see a real nasty decrease in your effective lifetime, linked to recombination near the surface. I think the initial papers he said at the surface, but I think he's now become more circumspect as well. And I think the evidence is pointing to it's not the interface itself, but something very close to it that is causing significant recombination. It's been observed in almost all surface passivation layers. We don't observe it in silicon oxide, a thermal oxide passivated layer, but I'm pretty certain you'd see it if you did a PCBD oxide. The caveat here is that the ALOX samples, where they're passivated with an ALOX layer with this nitride on top, are similar but different. I'll come to that at the end because they actually show quite a different injection level and degradation characteristics. It's definitely thermally activated. The higher temperature, the faster it occurs, and it does seem to have a link to the time scale with LeTID. So the faster LeTID goes, the faster this goes, and you usually can't see it until LeTID has started to recover. In some cases, you can describe it by a simple increase in the J0 value at the surface. So as you would typically model any increase in interface recombination. However, in several other cases, this doesn't work very well. Several cases you can do it, but what you see is an increase in your bulk recombination lifetime as well, which is a bit hard to explain physically. So speaking of which, here's some examples. This is from Kyung's work, who left us recently, and he looked at degradation in the dark at about 160 degrees. And what we can see, now I'm going to try this, bear with me. Okay, you can see at the moment. This initial degradation here, that you can see here, is one that we typically expect from LeTID, from the bulk degradation of cells after firing. So that comes down here. But this is not, this is something else. And what we can see is that there is a very strong correlation between the extracted surface recombination using the J0 method and the bulk lifetime here. So I'm arguing that this is not necessarily two separate defects. We don't necessarily have a bulk defect forming here and a surface one forming here at the same time, but it's one defect with its own injection level characteristics, which can be described by near surface recombination. That is, of course, speculation on my part. So we see it coming in. The other thing I'd point out, I mentioned it seems to, again, start just when the LeTID has started to recover. So when it's reached its minimum value, that's when we start to see the surface one kicking in. Although given the exponential timescales here, sorry, the logarithmic timescales here, it's not entirely convincing. There's also been observed dependence in the surface degradation rate by Sperber on the firing time and temperature. So if we take the case of LeTID, which hopefully people are familiar with, a lot of work's been done here. If you introduce more hydrogen, either by using a higher firing temperature or by using more hydrogen dielectric layers, we would expect an increase in the amount of LeTID you see. We see the same thing for the surface degradation, but to a much less pronounced extent. Now, ideally we'd have different temperatures here. I mean, 700 degrees we know is still good to release most of the hydrogen from a dielectric layer. We'd ideally like to see it down at 500 and 600 and see what difference that made. But there's still a little bit of dependence here on the firing process, which again, if it's hydrogen, we would expect that dependence there. The other thing that's been observed is that if you have an emitter present, so if you have a passivation layer on a undoped or a surface that has not a specific emitter present, we get very bad degradation. Sperber observed he put an emitter down, reasonably heavy by our standards. He observed much, much less degradation, almost completely suppressing it. So in the top left, top right there, you can see, top left for you, sorry, you can see in this case it's phosphorus emitters on a P-type structure. And again, the open circuits where we don't have an emitter present show this very bad surface degradation, whereas the closed symbols show far less degradation at the surface due to the presence of an emitter. Similar shown in the bottom left for you guys, where we're looking at boron diffusion on a P-type wafer. However, work at UNSW has found this is not necessarily the case. So some of Chen Denis's work and the other Danny's work later on have seen that when we do have an emitter present, with sufficient temperature, we do actually get degradation at the surface kicking in. So here we have a bunch of different emitter levels, and the area of interest is over here. So for the heaviest emitters, we see no degradation at the surface. However, when we have a very light emitter, 200 ohms per square and up, we start to see the surface degradation kicking in, and actually becomes much more pronounced with extra time, temperature, and a few other effects. So, if I move on one of Fiak's students, Zingeru, also observes quite bad degradation when an emitter is present with very high temperatures, so up to 250 to 450 degrees. He can actually see the rear surface of an N-type bifacial cell, where there's phosphorus diffusion present, degrades very markedly with extra temperature and extra time. So we can see degradation with these emitters present, but it requires specific conditions. So it's a slide without a graph, which hopefully everyone's pleased about. The basic theory of how LeTID and surface degradation might mesh together could be through, again, the action of hydrogen. So we would expect that hydrogen is released from our unstable forms in the bulk. That's what we believe leads to the bulk degradation, with hydrogen then becoming mobile and able to interact with other species and form recombination active complexes. However, due to the band-beneath silicon surface, we still expect significant redistribution of hydrogen to the surface. So while hydrogen move around and do various things, we do expect eventually most of the hydrogen up at the surface. And the question is whether the recovery of the LeTID is actually due to the bulk of the wafer being denuded of hydrogen, whether we actually move enough hydrogen to the surface that we no longer have as much in the bulk, we don't have our bulk LeTID, and we have an excess of hydrogen at the surface, which starts to lead to our surface degradation. Again, this is speculation, but it does fit with known results. So in literature, it's already been shown that the recovery of LeTID depends on wafer thickness, which the authors of that study interpreted either as metals moving to the surface or hydrogen moving to the surface into the bulk. how it fits exactly with hydrogen moving from the bulk back out to the surface. So you could fit it with any of those effects. And as I mentioned, we only see the surface when the bulk starts to recover. So it does fit at least some of the known behaviours of both LeTID and surface degradation. Of course, it's very high level and we need a lot more information, but that's the basics of it. So if we were to evaluate this theory a little bit further, there's a few key questions that I've investigated over the last little while. One is, again, we must expect a dependence on bulk material. Whether your material is P-type, N-type, multicrystalline, monocrystalline, should affect the rate of hydrogen transport to the surfaces, and hence should affect the rate of LeTID, which is known to do, and of your surface degradation recovery. It should be thermally activated as well. We also tried doing a higher temperature redistribution. So there's a bunch of anneals, as I mentioned, that cause the contact resistance that fix the LeTID. What effect do they have on this surface degradation, and can we actually match them up with the behaviour we'd expect if hydrogen is redistributing to the surface? There has already been a little study on the different bulk material and this type, different resistivities of P-type and one N-type. However, the difference is noticeable but not vast, and certainly couldn't be explained due to different conditions of the surface. Because they're all relatively lightly doped, and we're talking about under 80 degrees one sun illumination, under the same passivation scheme, the surface conditions for all of these samples were essentially the same. It's the bulk that is different. And so we're driving a difference in surface degradation due to different bulk properties. Internally, we've got more evidence on this. I think a fair few people will be prepared to say multi seems to degrade a bit faster in many cases at the surface. And certainly P and N-type, I'll present in a moment, shows very different behaviours, even though the surfaces are largely the same. So this is a breakdown of the splits of wafers I've done. So we've got quite lightly doped P-type and 1.19 centimetre N-type with two different passivation schemes. So we have the nitride and the alox nitride stack, and we fired all the samples. So if you don't fire the samples, you get no LeTID and you get no surface degradation. That was shown in Kyung's work, and I should have mentioned it more there. But, so here we want to fire it, we want to see it. We also want to see if we've, during the firing, degraded the dielectric layers somehow. If somehow we've changed the dielectric layers such that they subsequently degrade. So for some of the samples, we stripped off the original dielectric layers after firing and put down fresh dielectric layers before we started the degradation process. For other ones, we kept the same fired layer in place. So we've got layers that had a nitride at the start and have a new nitride, had a nitride at the start, have an old nitride, or had a nitride and were switched to alox afterwards, and similar with alox depositions. We then did degradation both in the dark and under one sun illumination at 175 degrees and observe what happened to our surfaces. So, depends on bulk material. So here we have on the right-hand side for you, the nitride passivated samples. On the left-hand side, the alox passivated samples. Unfortunately, this is about the only time they both behaved in a pretty similar manner. So the N-type samples degraded much faster than the P-type samples in general, and in particular, they degraded faster in the dark. Whereas for the P-type samples, the surface degraded faster under illumination than in the dark. This is actually quite good news because we can actually relate this back to some of the behaviour of LeTID, which I'll do on the next slide. The recovery rates do appear slightly different. So if you look at the right-hand graph, we can see that this nitride sample with N-type on it, in the dark has already started to recover after about 250 hours, which is quite quick as these things go, believe it or not. Whereas the alox sample is less definitive and it's taken 500 hours already. So the recovery rates might be different between the two schemes, which could be expected, but it's consistent with the same bulk driver of these effects being in place. And as I said, usefully, this has also been observed with regards to LeTID. So this is Daniel Chen's work, and basically in the dark, the N-type samples showed the LeTID degradation much more rapidly than P-type samples in terms of bulk degradation, and they recovered much more rapidly. However, under one sun illumination, N-type and P-type samples almost degrade and recover at the same rate, whereas P-type samples in the dark degrade much slower again. So this is exactly the same behaviour we saw with the surface in the previous slide, and makes sense in terms of the hydrogen model. Under sufficient illumination, the bulk hydrogen charge states should be the same in P or N-type, because we're driven by the quasi-Fermi energy levels, probably more so than the normal Fermi energy level under those conditions. And our simulations do say in both cases H plus should be dominant in the bulk and should be trapped. This does require assumption that the effective diffusivity of H minus is faster than the effective diffusivity of H plus. Now, there's, again, little evidence literature for either way, to be honest. In any case, what we always see is going to be the trap limited diffusion. So the most important parameter here is the H plus going to be trapped more effectively than the H minus? There are well-known traps for H plus, whereas the traps known for H minus are generally shallower traps, so might lead to a more rapid diffusivity. But that's one of the areas we actually want to investigate. The behaviour of hydrogen N-type silicon is not well known, and it's something we'd really like to investigate once we get some deuterated dielectric layers and we can see it. Now, the importance of dielectric during firing. Again, this was a nice result. It doesn't matter if you have what the dielectric is. If you have an unfired dielectric, so long as the wafer itself was fired and hydrogen introduced, it will still show surface degradation. So again, if you never fired the whole structure, no surface degradation. If you fired it with a nitride layer present, you'll see degradation, whether the nitride stays on or you replace it with a different surface passivation layer. So that was very encouraging. Somewhat surprisingly, the rate doesn't really change depending on that initial layer. So if you had an allox layer on there during firing, or a nitride layer, or you kept the same nitride layer in the silicon nitride case, the rates you can see over here, is this still working, are all pretty similar, whether in the light, okay, it's gone now, or in the dark. So with the open symbols, whether in the light, you can see they're pretty much the same, and in the dark, they're pretty much the same with the nitride passivation. Allox is a little bit screwy. So for the fired samples, where the nitride was fired in place, we show the expected behaviour. It's faster in the light than the dark for a P-type sample. And yeah, we don't see a big difference compared to what we see afterwards. However, when we put an allox layer down afterwards, although again, it doesn't matter if you used to have a nitride layer or used to have an allox layer on there, it's irrelevant. What we now see is with these new, recently deposited layers, samples in the dark degrade much faster and much more severely than samples that are under illumination. And this is aggravating because it makes it much harder to explain what's going on. But as we'll come to later, allox is a bit different and there's some quite fun things that might be going on there. Annealing, again, nitride behaves beautifully. So if you do this process we do, we know reduces the amount of LeTID we get. It also reduces the amount of surface degradation you get. So you can see here the blue curves are sort of unannealed, the red curves are when we've annealed them at 400 degrees for 30 minutes, which again gets rid of the LeTID problem. What we see here, the surface degradation is vastly reduced. Excellent. Allox samples, not so good. If anything, it goes the other way. So this is annoying, but also very interesting, because what it implies is that the surface conditions during this annealing are actually quite important. And when we come to the theory of what's going on, it actually makes sense because the surface passivation layer you have will determine your band bending during this high temperature anneal. So it will determine how well hydrogen redistributes that high temperature anneal as well as what happens during subsequent light soaking. So, is it plausible that hydrogen can cause these problems? Again, hydrogen is supposed to be a good guy in silicon and certainly shouldn't be causing defects that are so bad they drag down your entire lifetime, even when there's only a very thin layer of them. However, such defects have been reported. So, 1987, Noble Johnson and crew reported that in N-type silicon, when they exposed it to a remote hydrogen plasma, they formed some really quite nasty defects. And these were hydrogen platelets, which then became the base of the smart cut process. So you could form a plane, basically, of hydrogen defects and then lift off silicon using this process. So it is well known that you can form them. Also well investigated are the conditions under which you form them. As mentioned, they were observed in N-type. They were not observed in P-type silicon. If you introduce hydrogen with remote plasma to P-type silicon, it's fine. It doesn't make any difference. It certainly doesn't form these defects. And Nickel in 2000 put forward the theory that this is basically due to us needing hydrogen diamonds as precursors. So we need a mix of hydrogen charge states to form our dimers to then allow the formation of these platelets. And able to match that with the observed behaviour very nicely. So in the top left up for you guys, you can see a couple of these platelets that formed under the surface of an N-type wafer. And what's really interesting is they don't actually form right at the surface. There's a small gap before they form, and they penetrate deeper into the bulk. But if you think about the actual band structure of the sample, of an N-type sample, with no surface passivation during hydrogen introduction, the very surface, we have a Fermi level that is pinned to the middle of the band gap by the presence of defects. So we're in a situation where H plus is the dominant charge state for that structure. And then obviously as you go to the bulk, the bands bend up and we get a crossover point almost exactly matched with the depth we see there for where the hydrogen platelets start to nucleate. And we start to get a mix of H plus and H minus, and we start to form these defects. So further on, you can see again, further down in this graph there, the conditions under which it forms. I'm not, however, saying that platelets are what we're seeing in our samples. We're probably seeing something not quite that coherent and not quite that well formed. So if you look below, you see a paper in 2010 from Steingruber, where they actually observed defects in TEM close to a silicon nitride passivated P-type surface. And again, what you can see is the very surface doesn't look quite as bad as the region just underneath that. But again, the defects are much more distributed, much less coherent. So this is probably more likely what we're seeing, a build-up of hydrogen in that region leading to significant degradation. So with that understanding, we can model where we would expect these defects to occur in each of our cell structures. So if we have a nitride layer on P-type, an inversion layer at the surface, we can run our model, we can get fractions of hydrogen in each charge state, and we can see that if we're concerned about the product of the charge states, which we need for dimer formation, we would expect their defects to form within the first 50 nanometers, and usually probably around the 30 nanometer mark, which A, fits pretty well with injection level dependence, being modelled as basically a straight J naught, and if we go back a slide, matches very nicely with the observed location of the defects Steingruber found. I should put a caveat on this. We also have to consider gradients in hydrogen concentration. So because we expect this hydrogen redistribution and a build-up of interstitial hydrogen near the surface here and less in the bulk, that region is actually going to be even more exacerbated. The hydrogen products will be even higher there compared to the bulk region for the formation of these defects. If we look at N-type, under illumination, we expect something similar. As I said, under illumination, we actually have H plus dominating in the N-type material bulk. So again, under the effect of the inversion layer, when it gets more heavily, the bands get bent towards the surface, that's where we expect to find the defects. And again, it will be consistent with a J0 type dependence of our lifetime. In the dark, we get something quite different. So in the dark, under an accumulation region, under accumulation, the N-type material, we don't really have a sort of peak in the H plus, H minus product. However, we would then expect the most likely site to be where it sort of starts to flatten out, because that's where we start to get the biggest mix of charge states, and we would have the highest concentration, hydrogen concentration in our structure. So we actually expect quite different injection level dependence of these samples. Finally, with the light emitter, again, we have this crossover point, we have this point at which we expect a mix of charge states, but instead of being right at the surface, it's now much closer to the metallurgical junction. It's moved back a fair bit, and its location and the hydrogen gradient in that region are going to depend very strongly upon your emitter profile and the temperature you do it at. I think I'm up on time. So I was going to show you some injection level dependent lifetime curves, which more or less agree. I'm going to jump across to ALOX. So I mentioned ALOX is different in terms of what goes on. Sperber observed this and looked very carefully. Whereas with nitride, we see a significant increase in recombination near the front surface. There's something very nasty going on there, an increase in the number of defects there. With the ALOX sample, this wasn't observed at all. So if you look at the lifetime, the TCC is the minimum lifetime on a corona charge, basically under the flat band conditions when they measure the lifetime there. So the lifetime you get there is a very good indication of how good your chemical passivation of the surface is. And what he saw was, actually over the degradation process, that got better. So there's less recombination, less chemical defects near the alloy surface over time. What's changed is the field effect passivation. So they saw a significant decrease in surface charge during this degradation process, which explains their results perfectly, but then we have to explain why the change in surface charge is dependent upon the bulk material. So it still behaves, again, you can modulate it by using different material, different degradation. Something is moving from the bulk to the surface, or some interaction with the bulk's going on that's causing an allox layer to lose field effect passivation. There are two possible explanations that I know of in literature. One is that hydrogen is eminently capable of deactivating boron, so we may deactivate boron near our surface. The other one, which is more of a stretch, is auto-doping, the actual effect of the charge of the hydrogen itself when it builds up in sufficient concentrations. However, this is the wilder variety of speculation I'll put in here, and there's a lot more investigation that's needed to work out exactly what's going on there. And I'll finish there because I think I'm right on time, according to Ziv. So, summary. Yeah, we can simulate the redistribution of hydrogen, we know it happens. The question is how big an effect it is. So whether we're redistributing all our hydrogen or only a small amount, and how much is to blame for these effects that we're observing. And the behaviour of these effects allows us to infer that hydrogen is likely involved, but because hydrogen is such a pain, you never get full certainty. So one day maybe we will, but we'll see. I'd like to thank a lot of people in this room who've, unwillingly or willingly given results for me to use, and a few people over in Oxford who do a lot of the work on the contact resistant stuff as well, and the people who give me money, which is always nice. Okay, thanks guys.
Have you looked at, CV measurements to see the movement of, passivated dopants with your model, out from the surface, just from Schottky diets, just to compare if what you're seeing after this application of the bias coincides with the movement of the passivated dopants on any given waveform.
So you're talking specifically here about the contact resistance work in general? We haven't done a CV on it. I mean, we could do a CV across the junction, but we don't expect there to be a big change there. It would be possible, and we're trying to set up structures that would allow us to do that. So again, we want to probe the Schottky behaviour at that contact, which means we know that we need another contact in the emitter that doesn't degrade. So we're trying to develop structures that do that. We can have a look at it. My personal opinion is that it's unlikely. So in terms of we can see that hydrogen will deactivate phosphorus. That happens. But to significantly deactivate a large proportion of the phosphorus near that contact would require more hydrogen than I expect to be there. Let's put it that way. I think it's more likely it's actually going to passivate the interface states. But again, a CV measurement, once we have the structures, would tell us more there.
Yeah, I think it's just very easy to see it. Just from any given sample, you will introduce heaps of hydrogen, and you can easily push it away. It's just a matter of comparing what you've modeled with that behavior, and I think that's a very...
We can do it with need specific structures. Again, the problem is with the very high doping at the surface. I mean, we can deactivate 10 to the 18 phosphorus right near the surface. Doesn't make any difference because we've got 10 to the 21 phosphorus active. So it's making sure we have a significant enough effect to be visible using that method, which has been a challenge for some of the phosphorus deactivation.
Other questions?